A lonely star is just like a lonely person. However, when they pair up, their lives are filled with events. Stars, by exchanging mass, can make evolution, become variable stars, and produce bright X-ray sources. But occasionally, there are far more epic cataclysms, when the stars merge in a final, deadly embrace. Yeah, the single stars can only dream about something similar. Binary star, a system of two stars, occur quite often. In fact, the massive stars have a better chance of finding a neighbor. More than half of the massive stars exist in pairs. But among the low-mass stars, about a third of them are also binary star. In general, stars are gravitationally bound from the first day of existence. Gravitational captures sometimes occur only in dense clusters. This requires that three stars must come close together, and then, with a lucky coincidence, two of them will orbit around each other in a closed orbit, and the third will fly away, taking away the excess kinetic energy. Or the two stars must come very close to each other so that due to the colossal gravitational tides, they will get rid of the excess energy and angular momentum that prevent them from becoming a pair. Even if the stars were born as a pair, they don't necessarily have to be twins. The mass, which plays a crucial role in the fate of a star, can vary greatly among the components of a contact binary. Stars are fairly simple objects. Usually for a medium-aged star, knowing the mass is enough to determine all the other parameters, such as luminosity, size, and temperature. For example, 1/5 of a solar mass star will be a faint red dwarf. So, a binary star of different masses can sometimes look very beautiful. For example, at Albireo or Beta Cygni, one component of the system is orange, and the other is blue. However, the stars that compose the Albireo system appear to be twins only at first glance. On closer observation, they turn out to be triplets. The brighter orange star is in fact a binary itself, but this can only be seen with large telescopes. There are systems of not only 3, but 4, 5, 6, and even 7 stars. Although, their components still tend to split into pairs. Such binary space arrangements are not coincidental. They allow the stellar system to exist for a long time. Even if we try to create a triple star system, in which all the bodies are approximately equal distances from the common center of mass and orbit around it along intricate trajectories, such a process will soon be interrupted. One of the stars will be permanently thrown out of the system. The only reliable way to achieve stability for a multiple star system, for example, consisting of 3 or more stars, is to create it hierarchically. But this way, not all the stars will be able to interact and influence the evolution of their nearest neighbors. Only those at the very bottom of the hierarchy will be able to do so. The distances between the other components of the system are so long that they have no noticeable effect on each other, and they will evolve as single stars. For astrophysicists, the most interesting are close binaries. First, their interaction can change the mass of stars, the main determinant of their properties. Second, in the process of mass exchange, unusual bright sources of radiation can arise, which makes the life of the star more diverse and fascinating to study. Let's imagine 2 close stars, mentally draw a line connecting them, and calculate where the center of mass of the system is located. If we put a stone in it exactly, it will stay there. The gravitational forces from the 2 stars will be exactly balanced. If we move it toward one of the stars, it will orbit around it. In other words, each of the pair's components is surrounded by its sphere of influence, and the center of mass is the critical point, which is called the inner Lagrange point. The material in such a region orbits around one of the stars of the pair, that is, it is controlled by its gravitational field. Usually, stars are deep inside their Roche lobes, areas dominated by the gravity of one of the components of the binary system. Each of them securely holds its material, preventing it from leaving the surface. As long as this state of the system remains, the stars evolve as single stars. But in the later stages of existence, when the star becomes a red giant, its size increases by hundreds of times. As a result, there is a risk that it will be unable to fit into its Roche lobe, and then its material will begin to flow to the other star, so a contact binary appears. In a binary system, the more massive star is the first to reach the red giant stage. Therefore, the greater mass provokes faster evolution. However, at the beginning of the interaction, the smaller star of the pair begins to increase its mass at the expense of its neighbor. Thus, those stars that seem destined to become white dwarfs may end their days as neutron stars or even black holes. On the other hand, rapidly aging massive stars may transfer some of their material to a neighbor with less mass and look younger after that. This is how the Algol paradox can be explained. This binary star in the constellation Perseus, the less massive component, is at a later stage of evolution than the more massive one. Finally, the stars may even merge with each other. As a rule, if stars began to exchange material, it is not limited to a one-time action. Let's take two stars with masses of 12 and 9 solar, which orbit approximately 2.5 times the Earth's orbit around the Sun. The more massive star is the first to fill its Roche lobe, and its material begins to flow to its neighbor through the inner Lagrange point. In addition, some material is dispersed around the system and does not participate in its further evolution. When the matter exchange is completed, the first star is almost 4 times lighter, and the second is slightly heavier. In addition, the system has become much more compact and lighter due to the loss of material. After a few million years, the component, which was initially more massive, explodes as a supernova, turning into a neutron star. But this does not mean that its fate is now finally determined because it is in a close binary system. After a while, it is the turn of the second star to become a red giant. It, too, fills its Roche lobe, and its material begins to flow to the neutron star. During this process, it heats up to millions of degrees and a bright X-ray source lights up in the galaxy. While the overflow occurs, the orbit of the binary decreases in size. First, part of the energy of the star's orbital motion is carried away by the material leaving the system. Secondly, the alignment of the masses of the components leads to this. If we transfer a bit of its material to its faster-moving neighbor, it will slow down a little, and therefore come closer to the center of the masses. Decreasing orbit leads to catastrophic consequences for the system. A neutron star may fall inside a giant star and form the so-called Thorne-Zeitkow object. A single black hole is the final result of the evolution of the system. Although, separately, the single stars of the original pair could not have produced such a compact object. If we take the mass of the second smaller star, for instance, not 9, but 2 solar masses, leaving all other parameters unchanged, the fate of the system will be quite different. There will be no star merger in it. Instead, there will be several stages of material exchange, and a bright X-ray source will appear. Again, the second star will flow into the neutron star formed from the first one. But in the end, there won't be a black hole, but a pair of neutron star and a white dwarf. We can change the variables just a little bit more and again get noticeable differences in evolution. Thus, there is a huge variety of close binaries. Of all the phenomena of close binaries, perhaps, X-ray binaries are the best known ones. This stage occurs during the existence of many contact binaries, when one component of the system, becoming a neutron star or black hole, captures, or, as astronomers say, accretes, the matter of its neighbor. Accretion is a surprisingly efficient process for generating energy. If you take a brick and throw it at a neutron star, the impact on the surface will release as much energy as a powerful nuclear warhead exploding. Astrophysics stands out among the natural sciences in that it is impossible to experiment with the objects it studies. Therefore, researchers are happy to use any version of natural sensors. For example, if eclipses occur in the system during orbit when one star obscures another, it is possible to get an accurate estimate of their size. Nowadays, experts can easily say, the more massive the star, the more. However, some time ago, Measuring the stars' masses seemed like science fiction. And yes, how is it even possible to weigh a lonely gas ball flying in the void? It is a different matter if another object orbits around it under the action of gravity. In this case, by measuring the orbital period and velocities of stars in the binary system, it is possible to estimate their masses according to the laws of celestial mechanics. Just like almost everything in the universe, binary star collapse. There are two reasons for this. The first one is because of the villain star, whose close passing by the pair may lead to an exchange of partners. The second reason is that one of the stars may explode as a supernova. In this case, a significant amount of its mass is ejected into the surrounding space. The pair is held together by the mutual force of gravity. If more than half of the total mass is ejected, the system becomes gravitationally unbound, and the stars fly apart. In addition, supernova explosions are asymmetric. As a result, the resulting compact object receives a jolt at the moment of explosion, an additional velocity. If it is too large compared to the orbital velocity in a contact binary, it also leads to the breaking of the stellar pair. Therefore, although more than half of the massive stars, which then produce neutron stars or black holes, are included in contact binary, the fraction of binary among compact objects is much smaller. For astronomers and physicists, contact binaries are of great interest. Such paired dances and the complex relationships between them make it much easier for us to explore outer space. This is the star HD 139139. In terms of its class, it is a yellow dwarf, just like our Sun, so it is not surprising that they look alike. The Kepler telescope recently discovered it and sent the information to study. Analyzing the data, astrophysicists were extremely puzzled. In this star system, Kepler detected signals that resemble the tracks of as many as 28 exoplanets. Still, don't be surprised. It is not yet a sign that there are any exoplanets at all. Let's try to figure out what Kepler actually found. We'll start with a rather strange question: how many exoplanets can there be in the single star system? I'll tell you a little secret. There's no definite answer because no one knows for sure. Theoretically, there is no limit, because there is no law that says that. For example, a star can have a maximum of 20 exoplanets and that's it. Probably, the number of planets around the star depends on how much material is available for their formation, and how compact the system itself will be, so that it is also gravitationally stable. If a star does form many planets, they are likely to be predominantly small. Giant planets take up a lot of material, and they can prevent additional planets from forming in the rest of the system. So far, our solar and Kepler-90 are the two systems that have been found to have the most planets, 8 each. It is probably possible to find a star with dozens of planets in a stable configuration. It remains for mankind to find out how probable such systems are. Now, let's go back to the star HD 139139. It is located in the constellation Libra and is 350 light-years away from Earth. The star is slightly larger and brighter, but identical in temperature and much younger than our Sun. It is only 1.5 billion years old. By the way, HD 139139 has a companion star, a red dwarf. So, the Kepler Space Observatory discovered this yellow dwarf and recorded 28 strange transits that would normally indicate that there are planets orbiting the star. But perhaps we're talking about something like a whole new type of sunspot. We will talk about that later. Let's explain what transit is. The transit method of detection is the most popular one. How does it work? The principle is simple. When an exoplanet passes between its star and an Earth observer, the brightness of its luminous disk is reduced by a clearly detectable value. Thanks to this, it is possible to estimate the size of that exoplanet. Using this method, the Kepler Space Telescope managed to detect thousands of exoplanets before it finally shut down in November 2018. However, the observational data is still being received and continues to be studied on Earth. Such is the case with the star HD 139139. Kepler observed the star for 87 days, and during this time it recorded 28 transit signals, which indicated that exactly exoplanets orbit around HD 139,139. The shape of the diagrams of changes in the luminosity of the star during the transit of exoplanets on its disk differs from the shape of the graph for transits of dust clusters and other objects. Only 2 of them were commensurate with giants like Jupiter. The size of the other potential candidates was small but slightly larger than the Earth, and they all resemble each other. That is, 26 exoplanets commensurate with Earth. The discovery is amazing and very rare. But the chances that these are really planets are very small. The fact is that in such a short time, 28 planets can pass between their star and Earth only if they are all orbiting very close to the star. Planets as distant from their star as those in the solar system are unrealistic to pass between their star and a distant observer in such a short time. The farther a planet is from its star, the longer the period of its orbit around it. Therefore, an observer from another system can see the transit of all planets, for example, in the solar system, between the Sun and a distant observer, only after many years of waiting, but not after 87 days. However, if the planets of the system HD 139,139 really rotated close to their star, their transits would have had time to repeat in 87 days, but this didn't happen. The duration of the transits of each object was different, it ranged from 45 minutes to 7.5 hours. So the scientists realized that we are talking about different signals. But if these are not exoplanets, then what is this strange phenomenon? There are several assumptions, or it's better to say hypotheses. As we have already said, HD 139,139 has a companion star. Astronomers have suggested a model in which the planets in this system are common, that is, they orbit both HD 139,139 and the other star. This could explain why the transits were not repeated. If the planets have to make a wide circle around the 2 stars, the transits don't have to repeat quickly. Nevertheless, this option looks rather dubious. It doesn't explain how the 28 planets were able to pass between one of the stars of the system and an Earth observer in just 87 days. Another hypothesis explained the mystery with the help of numerous asteroid clusters, which could mimic planetary transits in case of sufficient size. However, scientists were forced to reject this option as well. Such asteroids had to be unrealistically dense. In addition, there had to be too many of them. As a rule, if none of the scientific explanations can be applied, then science fiction comes into play. So it happened in this case. There is an assumption that non-periodic transits can be connected with the activity of hypothetical extraterrestrial civilizations, which can build something like the Dyson sphere. Dyson sphere is a megastructure. Imagine that some advanced civilization managed to build a shell around such a huge object as a star, and this structure absorbs all its energy. Hypothetically, it is possible. However, if HD 139,139 has such a structure, then the civilization that built it is unlikely to come from this very system. Remember, the age of the star is 1.5 billion years. When our Sun was that old, the Earth was still inhabited by single-celled life, and it is very doubtful that life developed much faster near another yellow dwarf. Previously, astronomers have already found stars whose luminosity varied strangely due to the transit method. For example, it was characteristic of the so-called Tabby star. To explain its anomalous non-periodic transits, astronomers have also hypothesized about the megastructures of another intelligent species. However, long-term observations of the Tabby star have shown that its luminosity varies greatly in the visible and ultraviolet spectrum range and is much weaker in the infrared range. It seems as though the star is surrounded by dust clouds. The dust well absorbs shorter wavelengths of visible light, but poorly absorbs the longer infrared wavelengths. Therefore, the hypothesis about the artificial nature of the fluctuations of the luminosity of the Tabby star is not so popular today. Regarding the star HD 139,139, the researchers focus on another explanation. They consider unusual spots on the disk of this star, which have a size close to planets, as the most probable scenario of these non-standard transits. This option also has drawbacks, because the spots on stars like the Sun exist for a relatively long time and must reappear in the telescope's field of view during the rotation of the star around its axis. However, the actual transit signals from HD 139139 are non-periodic. In other words, if these are indeed spots on the star, they should have a lifetime of only a few hours and disappear before the star makes a complete rotation around its axis. Examples of such short-lived spots on stars of this class are not yet known, neither from observations of the Sun nor from studies of other yellow dwarfs. If the explanation of the oddities of the star HD 139139 really comes down to spots, we are talking about the discovery of a completely new type of spots. During its mission, the Kepler telescope observed 500,000 stars, but it had never seen one like this. Scientists still don't know what to do with it. They suggest pointing the TESS telescope to HD 139139 for further observations. It's even planned to expand the mission for this purpose. In any case, the answer, I believe, will be found, and it will be very simple, as usual. The space is full of mysteries. Some of them are still unsolved, while some have already become well-known sensations. It's not a secret that most of them are related to the stars, which have always attracted both astronomers and those far from astronomy with their magnitude and inaccessibility. Our Milky Way galaxy is home to hundreds of billions of stars, and each of them is particularly unique. But it also has many neighbors, and the Large Magellanic Cloud is one of them. Even though it is smaller, and its diameter is 10 times smaller than the one of the Milky Way, it still may surprise any of us. This is the galaxy, hosting the unique binary stars VFTS 352, which have relatively recently been found by astronomers and have become an incredible astronomic discovery. Why is this star considered so special? Watch this video to get the answer. The first time these binary stars were observed was in October 2015 by an international group of scientists. And today, it's still one of the most curious and unusual binary stars known to humanity. To examine it, the scientists used the Very Large Telescope, the giant instrument of the Paranal Astronomic Observatory. It allowed scientists to see clearly that VFTS 352 is not just a star system, but an extreme binary system. The astronomers found these binary stars in the constellation of Dorado in the Tarantula Nebula, actively producing young stars in the nearby universe. By the way, this nebula possesses the most massive star discovered in 2020, which you may know as the R136A1. If you'd like to see a video about this star, write it in the comments. By the way, you all could have seen this pic or GIF. This computer model was designed exactly on the basis of the VFTS 352, and its objective was to show this system's uniqueness. You may often see these graphics even somewhere you don't expect to see any star system, which is quite an interesting fact. We've got a bit distracted, but now let's get back to the VFTS 352. There is a lot to tell about it, even though it's so distant from us. The distance between our planet and these binary stars is as much as 160,000 light-years. Both stars of this system are white and blue and belong to the spectral type O. They are very young, and, as a rule, the stars of this type are no older than a few million years. The stars of this type are rare, but their brightness makes them visible from a very long distance. The VFTS 352 system is unusually massive. Its common mass is about 57 solar masses, while its whole radius is about 7 solar radii. Meanwhile, the temperature of the star's surface may reach 42,000 Kelvin. Just to compare, the Sun's temperature is just 5,780 Kelvin. But actually, this star belongs to another spectral type. To measure separately the mass and temperature of each star are still quite challenging as the stars are too close to each other. But what is remarkable is that both stars are roughly the same size. It's really rare for the binary stars since usually a companion one is fueled by its bigger sister feeding off the star material from its surface, thus rejuvenating its own subsoil. We may call it star vampirism. Bright, massive, and extremely hot stars of the system VFTS 352 are characterized by the quite short distance between the centers of each object, which is only 7,458,048 miles. Speaking of the similar binary stars, this is quite a short distance, allowing them to adjoin their atmospheres, forming a kind of bridge. To compare, again, the distance between Mercury and the Sun is a bit less than 36,047,234 miles, which is almost 5 times longer. At the same time, to complete an orbit around the common center of gravity, the VFTS 352 system needs a bit more than 24 hours. Such a star system hasn't been seen ever before. The main reason is that this phase is usually passed by stars quite rapidly. That is why finding them requires quite an effort. As we speak about the binary stars, I'd like to make a little aside and briefly tell you that there are a lot of systems consisting not only of 2, but 3 and even more stars. Such systems we call multiple. For instance, one of the brightest stars in the night sky, Alpha Centauri, is a triple star system. Most multiple stars are binary, although there are systems including 5 or even more components. In the case of the VFTS 352, we have a contact binary system of stars bound with the gravity power and masses orbiting the common center. But in general, the components of binary stars are different in terms of their spectral type and physical parameters. That is why we usually divide the binary stars into 2 types: the stars with mass transfer and the stars without it. The first type, transferring mass from one to another component, is called a contact binary star system. Such systems are typically located deeply within their Roche lobes, the regions that have dominating the gravity of one of the binary system components. Each of them reliably keeps its material, preventing it from leaving the surface. As long as it works this way, each star of the system evolves as a single star. But in later life stages, one of the stars becomes 100 times bigger. As a result, there may be not enough space for it within its Roche lobe, so its mass starts transferring to another star, forming an interacting binary star. Roche lobes are bound to the stars, while the material which lies outside the Roche lobes creates a common Roche lobe overflow and transfers from one star to another. Therein lies another peculiarity of the VFTS 352 system. Thanks to the similar scale of stars, the material they need to exist is divided equally between them. It means that about 30% of the star material is common for the 2 components of the system. That is why we may often hear the word combination over contact binary star system used for the VFTS 352. The mature close stars may have absolutely different life scenarios, and it's difficult to say how this or that system will end up. Astronomers suppose that the binary stars VFTS 352 may follow 2 scenarios. One of them leads to the merging of the 2 stars, resulting in the formation of a highly magnetized giant single star, while another one suggests avoiding merging the VFTS 352 components, which is possible if the star's masses are thoroughly mixed, and each star becomes a compact one. This scenario would be a new development path of a unique binary star, totally different from the usual evolution process. Most probably, the components of the VFTS 352 system will explode as supernovae and form a close pair of black holes emitting intense gravitational waves, which will later result in their emerging in one massive black hole. This evolution process may become a real sensation in astrophysics. But whatever it ends up with, the star system VFTS 352 has already made scientists look differently at the evolution process of massive overcontact binary stars. The stars are already poetized in many works, and who knows? Maybe these overcontact binary stars will inspire poets to write new wonderful pieces, which will later become classics. But for now, they inspired the journalists to call this unusual and apparently unique tandem the kiss of the stars. And, you know, it makes sense. I think you'd agree that the stars are really special phenomena. And the sky full of stars is an indispensable part of romantic for those who are in love and are so inseparable as the binary stars of the VFTS 352.